So up to yesterday, we figured out the convergence of geometric series, right? And basically geometric series depends on the common ratio R. If R is a geometric series, if R, absolute value of R is less than 1, then this is convergent, right? Otherwise, it's divergent. It's not like you can actually give that as an answer. AP might have that as an answer, but no, it's not good enough for me. You have to find the partial sum and take a limit and show me that is convergent, infinity or finite number. Okay, that's my requirement. So don't be giving me that kind of thing, right? And today it's called the integral test. Do you remember P-series test? Wait, did she get to chapter 20 during the pandemic or did she run out of time? So, well then you do remember forgetting P-series? What is a P-series? P-series is something that looks like this. And usually 1 through infinity of 1 over n to the p power, right? Right, so what did that chapter 20 packet tell you about the convergence of this P-series?
If P is greater than 1.
If P is strictly greater than 1, then this is convergent. And if P is less than or equal to 1, then this is divergent, right? Okay. Remember that? Or remember forgetting that? If you forgot, I have a good news. If you remember that, I have a bad news. Guess what that news is? You cannot use this either. Neither of this explanation is allowed, okay? Because up to last year, you didn't know any better because you did not know what integral was. You didn't have enough integrity to show this. So only thing was, well, trust me, the teacher, and memorize it, right? Now y'all have enough integrity to prove your case. So not allowed, okay? Video evidence, don't tell me I never warned you, okay? This is a video recording, not allowed. Okay, so this is a P-series when P is equal to 1, right? This one is known as harmonic series. And or you can just say P-series is a P. It's a case of, my computer is not working. P is equal to 1, okay? And those of you musicians, you guys know what harmonic overtone series are. If you play brass instrument, you really know what that is, right? So it has to do with a half. If you cut the string, I play guitar, so I kind of know this, or violin, if you just put exactly half of them, that's an octave, and the third is it's like fifths, I think, and then you can build pretty much anything out of it. So it has to do with the music, but that's where the name comes from. It doesn't matter. So you were told last year, this thingy is divergent because P is equal to 1. But can we prove it now? Okay, that's our task. And I have a graph ready. So let's bring this thing in. Okay, this is y is equal to x squared graph, and I'm gonna change this, rescale it, so I'm gonna make this side longer. Good. And make it a little bit wider. So this is 1 and this is 1. So far so good? Okay, I'm gonna make a copy of this. This computer is, oh boy, I hope this thing lasts. Okay, that much should be enough. Okay. shove that thing aside, and I'm gonna paste the graph right here. Oh, that's big. So here's a graph. Okay, now, do you remember comparison test with the two improper integrals? Yeah, it's kind of like that. Because you have to remember integral still is infinite series, isn't it? Yes, it is. So I'm gonna be clever and draw some of the rectangles here. Watch this. Okay, this side is 1 and this side is 1, right? Somebody tell me what the area of this rectangle is. That was not a trick question, right? Okay. 1, too late. I already wrote it. Okay, chance to redeem yourself. Here we go. Okay, somebody tell me area of that rectangle. 1/2. 1/2, right? These are not trick questions, okay? Because this function is f of x is equal to 1/x, that's the key. So if this is 2, do you see this is 1 and this is 2 right there? So it's 1/2, you know what I'm saying? Okay. Okay, now you're feeling very confident about the next answer, right? So what's the answer to, what's the area of this rectangle? Oh, come on.
1/3.
1/3. Next one? We'll just throw one more to make the notes pretty. And this is 1/4, isn't it? Right, and this index right here, where these x values are, matters a lot in the picture, soon to show up. Wait a minute. So this P series, harmonic series, can be represented by the area of these infinite rectangles, right? And there are infinitely many of them. Good. And now you want this to diverge. So my question is this. If we compare that with area of this integral 1 to infinity, what does that look like in this picture geometrically? 1 here is the starting point, right? Dividing line, and that represents this area underneath the curve. Good? Do you see that? Which is greater? Just by looking at it. It's not a trick question. Which is greater area?
Rectangular approximation.
Right? I mean, this is exactly what that was, rectangular, left rectangular approximation, wasn't it? Wait, but from chapter 8, we know this thing is infinity, correct? Did I just prove that this thing diverges? Oh yeah. So this is a direct comparison test, but we are comparing the infinite series to an integral now. So this one now, let's review chapter 8. You have to rewrite it like this. Proper integral is the first thing you do. And then 1/x dx. And this thing still is limit of b approaching infinity of, this is ln, and are we sure? Because that negative 10-point rule still applies. So we have to be very sure before you write ln. And that is ln b minus ln 1, correct? ln 1 is 0, ln b approaches infinity as b approaches infinity. Good. So this is equal to infinity. So what have we proven? I just have proven this P series, when P is equal to 1, is infinity, is divergent. Good. Okay. Well then, let's look at the next case, shall we? This is the next case. Well, now P is equal to 2. What is our correct answer? Does it diverge or converge? This thing converges, right? P is more than 1, and that was the criteria. We just cannot use it, but we can still know the answer before we start. Okay, let's look at the graph. Okay, so I'm going to modify this graph now to be 1 over x squared. Oh, almost the same thing now, isn't it? It's like it got a little skinnier. Okay, I'm going to stretch this side out more so I can throw these things. Okay, I'm going to copy this. Well, let's go back here and let's put it here. This thing always turns out to be humongous. Okay, let's put them here. Okay, now, so the integral from 1 to infinity, of course, is that area starting right here, right? If we draw the rectangle same way, like this, this area is 1, isn't it? Oops. This computer. Seriously? Go back up. That area is 1, right? And the next rectangle will be right here. And some of you already see, no, that's not right. And this area is 1 over 2 squared. Now, what are we doing? How am I comparing this thingy? 1 over n squared and versus 1 to infinity and 1 over x squared dx, right? Do you remember from chapter 8, this is convergent integral? This, in fact, is equal to 1. But which is greater? Which area is greater according to the picture that I have drawn?
Rectangle.
Wait. This way, right? Exactly same way as before. So, and this will eventually turn out to be 1. What have I proven?
Nothing.
Nothing. Oh, okay. So scrap that idea. So in order for this comparison test to work, we want that direction that way. Right? But no, it's sticking above, right? So that ain't gonna work. So what do we do now? Well, one might think, well, why don't we move this rectangles over? Like that. This is kind of too big. Hold on, let me resize this. How do you like this idea? I'm going to draw a few more rectangles now. I guess one more. Say we have like this. So this area is 1, and this area is 1 over 2 squared, and this area is 1 over 3 squared, and this is, so this is 1, 2, 3, 4, and this area right there is 1 over 4 squared, isn't it? That's tiny. I'm going to write it here. This is 1 over 3 squared. Good. Oh, yeah, that works. We can just shove it underneath. We use right rectangle approximation. Okay? There's another problem with this. Can somebody figure out the problem? What is problem now? That looks perfectly all right. While you do that, I'm going to work out this right-hand side. Let's see who's brilliant. Limit, and then b approaching infinity. And then we write this thing as x to the -2 dx, because if you put ln 1 over x squared, that's -10 point. Right. And this is x to the -1 power, therefore negative. Do you see it? Oh, this is from 1 to b. And 1 to b, and use plumbing professor. So we plug in 1 first, 1 minus 1 over b, and 1 over b dies. So we have 1, as we predicted before, right? This side is. Okay, Ethan, have you found out what's wrong with this whole thing?
Well, I was going to say that the very first rectangle is kind of iffy because you're starting it on x equals 0, which is an asymptote, but then in the summation in the problem, it looks like they start with n equals 2, not n equals 1.
Yeah. You see the problem with this first rectangle? So as of this thing is already 1, and we are saying that's less than or equal to 1. That doesn't work because these two alone is more than 1 already, right? This is not a fair comparison. You have to understand where the starting line is. It starts from 1. Okay, I'm going to draw that line. Starting line is right here. This is our starting line. Right? It starts at 1. So you see, integral area starts from 1 and on, and rectangle area starts from here. So it's like we have this inequality cannot be true. So how do we adjust it? Some people do 1 plus on this side, but better way in order for the future purpose is we make this thing start from 2. You see, there's a fair comparison now because all the rectangles that starting is underneath, and then we are counting it from this one. All of this is less than or equal to 1 is what we're saying. You get it? And then when we conclude at the bottom, we can say, therefore, our original, because the first, not having first few finite term, we don't care. We just say this is less than or equal to 2 now. We just add that one back here. You get it? See, infinite series convergence only care about the tail end of it. I mean, you can have the first 2,000 terms out. That's still a finite number. And from 2,000 first to the infinity is what matters. You get it? Now, most books, NAP exam, will just never establish this inequality and say, oh, integral test and just do this much, and then, yeah, it depends on, guess what how I'm gonna grade it. I'll deduct a point unless I see a proper inequality with a proper indexing. Okay, so I demand this. This is critical later in life, but like this chapter. Later, when we do error estimation, this is a critical skill. So I want you to know, so this is requirement. Okay, so pay attention, watch this video, make note of this. Don't say, I thought it would be okay because the book. I don't care. Not good enough for me. Okay, good. And then we like to now say, well, let's establish that. For what p-value does p-series converge then, right? Let's just prove p-series test. Even if I prove it here, you're still not allowed to use it forever. This is just to give it to inferior minds, okay? Because somebody had to come up with these kind of criteria. So the p-series. P-series convergence criteria looks like this. Okay, so P-series will start it with 2 and 1 over n to the p power. I'm going to zoom in a little bit. And this needs to be less than or equal to from 1 to infinity. And you replace it with x like we did, right? Some people have put n and integrate. That's kind of annoying. Now, here we have this direction like this because we are now assuming p is more than 1 because we have done when p is equal to 1 case already, and that turns out to be divergent. That one is a different, you have to treat that separately. So in this case, p is not equal to 1, okay? It's more than 1, but how much more is enough? Okay? Any question? And do you see why this thing is starting from 2? It's like this is when p is equal to 2 case, and you have to cut it right there. You know what I'm saying? This first rectangle has to be taken out in order to make it a fair comparison. Okay, now, then all we have to do is to evaluate this integral. So we write it as proper integral b approaching infinity and integral from 1 through b, and then we'll rewrite it like this. Good? Let's make it a little bigger. Okay, and that is limit of b approaching infinity of, how do we do this? Well, we add 1, good, and then we divide by that number, correct? Is that how we integrate? Using power rule? Usually this is like 1/3 or like 1/3 or 4th, but this is in terms of p. And then we substitute b and substitute 1. So what we have is, scroll a little bit, scroll down. Okay, so what we have is b to the 1 minus p over 1 over p, 1 minus p, and then we put 1, right? So we can just write it like that, eh? Say yes. Who's lost? Y'all with me? Okay, now we want this thing to die. We want this thing to die, right? Because the b is approaching infinity. What is the only way this dies and gives me this? Right, this. Or do you like, since p is more than 1, should we just make it like that? And this is not a misspelling, right? If and only if. What is the criteria? Now somebody tell me. You want this thing to be exponentially decaying. Well, not exponential function, but this should die out. That means this needs to be in the denominator, correct? That means 1 minus p needs to be negative number. You get it? It needs to be a negative exponent somehow. It could be 0.1, but negative 0.1. You know what I'm saying? You with me? And then, whoa, that of course tells you p is greater than 1, right? Your p series criteria. See, today's content is adding the p series up, first 10 terms, okay? And then we have to estimate the error, right? Now, and then this is a very difficult question. In order to achieve such an error, how many terms does it require? Right, okay, so before we start programming, because young programmers these days, they just start typing in and coding, right? That's not as recommended. This is the old-fashioned programming, the way I was taught. I've never taken real comp sci programming classes, but I am an applied math major. I had to do a lot of heavy dose of programming in order to solve math equations. So you first start with a pencil, okay? So let's just look at this. S sub 10. Let's just write down what that is, right? Because the partial sum, right? First 10 terms, that's what we call S sum, they're called partial sum from pre-calculus, correct? So that is 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus dot dot dot. And then what is the 10th term? It's not a trick question.
1 over 10 cubed.
Oh, I already screwed up. 1 over 10 cubed, right? That's easy to see by substituting different n values here. Okay, then. Now then. And then you're thinking, even if you have a calculator in your hand, like you, right? This is a lot of work. And for your homework, you have to do a lot of these. That's time consuming, and there isn't really no education value for you to do this over and over. You know what I'm saying? This is where we teach the machine to do the dirty, repetitive work. You know what I'm saying? So this is where the program comes in handy. So are your calculators fired up and ready? Okay, probably I'm gonna have to restart all of this. I'll just clear every single line. Wait, do you still remember how to create the program and name it? That much? So do that much. Let's name your program P series. Once again, we can only use up to 8 letters. This is our old-time program. Okay, once you're done, then I will start coding with you. Okay, are you there? Who needs a little more time? Okay, so we are all here. Now let's start. Purposely, I'm going to leave a line because I'm purposely going to miss something, and you get to point out what that is. So, what does all programs have in common? All programs must have these two things. And what are they? Most basic things.
Input and output.
Yes, input and output would be it. Otherwise, it's useless add, isn't it? Right? Okay, so let's start there. So hit the program button. And then inside the program button, wait, I'm standing my computer up so I can see it better. Not these, but input output, just right scroll, and number 1 works if you want to be fancy, and there's about number 2. It's better for us since you're the only user, right? Prompt. Okay, what are we putting in as an input now? One of the things that you need is the terminating term, which we usually call K, right? S sub K. In this case, 10, right? Otherwise, because you usually have to start by computing first 2 terms to test out, and then 3 terms and see, and you have to work this out with a hand and make sure your program is correct, right? So let's have K to begin with. So alpha key and then press K. Good. So that's your first input. And we'll improve this and make it fancier. Okay. But let's just do that much. And then do you guys remember the for loop? Whenever we need to repeat things over and over. Okay, let's come back here. Before we do the for loop, do you notice that your series is just a bunch of sequences added up, right? This thing being your AN. So it's convenient to have AN on a side, and let's just decide. In this case, AN is really easy, isn't it? That thing is our AN. See, bunch of, if we add up all of the sequences, that becomes the series, correct? Okay, so we have to put in AN to compute. So let's just create AN here. So AN is 1 over n cubed, right? So let's do for loop first. Number 4 is for loop. For loop meaning you repeat. And I put if in that crate. Okay, let's try that one more time. For loop, for. Okay, and our index will use n. N, this is our indicating what our index is, because Cn is part of our sequence, so we need to know what index. Some people use n, some people use I. I use these two generally interchangeably. And then starting from 1 and to my terminating term k. You get it? You with me? Whenever I do for loop, I always skip, enter a bunch of empty lines and put end here. So program number 7 is end. Okay, whenever you start a for loop, you have to tell the machine which part of this code to repeat. So machine is going to repeat whatever's between these two, for and end, over and over and over. Okay, so it's my habit to just put for and bang, and then I'm gonna fill in what's between. With me so far? Who needs more time typing? Okay, moving up now, then your sequence. Usually if you're a real programmer, then it's A is equal to this, but this machine is kind of retarded, so we'll put it this way, 1 over our n. N is this index, and they have to match, cubed. With me? And then we want to store that into letter A. Okay, that is exactly this thing. Good. Whenever you program series, always separate the sequence and the summation. Okay, don't try to put everything into one, because later we have to modify these things and debug it in case there's a bug, in case something screws up. So this makes it easier for you, okay? You with me? Any questions on what's going on right now? Okay, then here S with summation, our S, let's introduce S. I'm gonna put alpha S. So I'm gonna do this plus our A, and I'm gonna replace my previous S value with this. Does that make sense to you? Okay, those of you who have never coded before, let me explain. When our n is equal to 2, so we are computing this, my S already has 1 stored in it. So this is like a recursive formula. Looking at S as a sequence, and this is recursive formula. You know what I'm saying? Sn plus 1 is equal to Sn plus A n plus 1 kind of thing. And then I'm adding this thingy and replacing it. And once my n is 3, then my S has these two terms added up already, and then I'm going to add one more term and replace the whole thing. So it updates each time. Who's confused about this recursive formula part of S? You all with me? Okay, then we probably want to have the answer displayed, right? Okay, I think we talked about this before. There are a couple of competing ideas. We can put display here, or we can put display here, and each method has advantage and disadvantage. Which is better for now at the moment? Do you want it here or do you want it here? How are they different?
Inside, so we can see if there's a mistake.
See, if you put it here, then each time we go around the loop, it's going to spit out the answer. So you can see a bunch of different answers, starting with index 1, 2, 3, 4, 5, running total. That slows the machine down, right? So initially you want to put it here so you can see it. I usually leave it. But if you're a real programmer writing this for the customers, then later when you're done, then you put it here so that the customer, the user, only see one answer at the end. You know what I'm saying? So we'll put it here. So display output, because we have input and we need output. So let's press program button, input output, scroll right, and number 3 is display. Okay, the way I do display is this. Open set bracket, set brace, or whatever you call it, this thing, not the parentheses, second and parentheses, that brace. And then I'm gonna put n, so that I know that which index is computing which partial sum. You get it? And then I'm gonna put s. And then close the brace. Good. Okay, looks like we are done, except I'm missing one little thing. What am I missing? And it should go at the top. My style is I always put this missing thing at the top. Somebody in ComSci tell me, huh?
You need to define S.
Define S, right? Well, this program does not really require that, but we at least have to initialize what that is. Okay, after you type it in, then I will show you explain what that means. You have to assign the value 0 to S. Okay, now, why is that? S is usually probably 0 for the moment, but as soon as you run this program once, whatever the S value you computed, the machine is going to remember it forever until you run it again. So instead of restarting from fresh 0, it's going to remember and just pile it up, and you never get the right answer. You don't want that. So whenever you have a variable, many programs actually make you declare the variable. This one doesn't, but you have to at least initialize it. This is a good habit in all programming. Okay, and initial value usually is 0 or 1, depending on whether you're adding or multiplicating. That makes sense to you? Then you're thinking, why didn't you initialize A? Well, I could have, but I don't need to, because each time I enter the loop, I'm recomputing the A value. Fresh, right? This thing goes into A, so I don't care what it was before. But in case of S, there might be some thing in the memory slot of this thing called S, so I have to get rid of it. Good? You with me? Okay, I think we're done. Shall we test it? Yes. So it's an autosave, so you can quit. Okay, and then you press program, and you choose this one, P series, enter, and enter, execute P series. Okay, shall we just calculate 2 of them so we can compare it with our hand calculation? So let's put 2. This is why I always put the K as an input. Enter. Is that correct? 1 plus 1 over 8. Is that 1.125? Yes, it is. You know what I'm saying? So now I have enough confidence to, and you don't have to go to program. If you just press enter, it executes the previous command. And then now I can put 10. Then watch what happens. See, gives me the running total. You know what I'm saying? And then remember, in order to get rid of it and have just one last answer, then you move the display out of the for loop. Okay, I'm gonna compare this with my Dropbox note. 197532, 19753. Yep, this is correct. Okay, so old-fashioned programming, you always do this by hand, and then you write this in. Okay, so this now I know is 1.197532. Okay, always put 6 digits with a squiggly equal to, because some of you, wow, like giving me 2 decimal digits on the test. Dang, I took a lot of points. You still do that? Wow, how long have you been here? Okay, now, before we go to error estimation, I like to modify this program so it's a little more user-friendly, because you have to do this over and over with a different p value. P series, remember this is p, right? And to the p power. And you don't want to modify the program each time when you do this. You know what I'm saying? So instead of doing that, let's go back and edit. Program, edit, and our P series. Okay. I want to have another input. So instead of here, I'm going to have that first. So insert. Okay, guess what I'm going to call this input value variable? My God, you kids without any imagination, right? And you really don't need space. How about that? P series, so I need P, and our P is 3 at the moment. You know what I'm saying? That way, if you're doing homework and have to run different P series, you don't have to come in and edit this thingy 3 here, right? So, and go down here. So instead of 3, I'm going to put P there. You see how much convenient that will be? You get it. Any question at the moment? Good. Okay, so this will be our convenient P series program. You may use it on your test, if I ever put this on the test. I mean, you definitely need to use it on homework, otherwise your homework will be really, really, really long. Thing about program is, if you only have one problem to do, then you either do this or write one program, and like amount of time is about the same. But as soon as you have more than one problem, like 2, you're cutting down your time by a lot, because this is tedious to type it in. You know what I'm saying? So you rather want to write a program and let the machine do it. You just need to do it by hand maybe once to understand what's going on. Alexandria, do you have a question?
Yeah, wouldn't you ever want to start the index at like 2? So would you just go and edit your actual program to do that?
What? What was that?
Like when you ever want to start counting at like n equals 2?
Oh, I'm not understanding the question.
Like you start with 1 over 2 cubed, 1 over 3 cubed, like sometimes.
1 over 2 cubed? Oh, if you want to start this thing with a 2.
Yeah.
Then what you do is you put another, this, if you start this thing with 2, then this thing will start from number 2.
Yeah. Just.
But you can put another variable here, like beginning and ending, like I and K maybe. But most series, do they do that? If you do, it is a quick modification, right? Just this, and then enter that variable here. But I'll just leave it for the time being. I think most of it in our homework starts with 1, right? Okay, anyway, that's how you do it. Good, excellent question. Okay, any other questions? Okay, let's run this and see what it looks like. You want to move the end out, display out here or not? I will just leave it. So quit, and we'll execute the same thing. P series, now I see it's asking me for P. Right, and we can put 3. And then K, once again, 10. And execute, and we get exactly the same answer. You get it? But now it's more convenient to do your homework with, because you have different P series with the different P values. You know what I'm saying? Any question before I go to now the integral part, the real calculus? Okay. I think I'm gonna put programming on your second quiz. So it's not optional, you have to learn how to do this. Okay, I'm gonna quit this. And then let's come back to our calculus now. Okay, so we got this. Now we have to estimate the error R sub 10. Now, what does that even mean, right? So this is your part A, and then part B. R sub n, the way it's defined is really weird. So your infinite sum S is going to be your, in our case, A1 plus A2 plus dot dot dot. This is A1, A2, A3, right? Plus A10. Up to that much is our S partial sum S sub 10, isn't it? Gonna squeeze the space down here. So this is what we call the S sub 10 we just computed. Okay, and what's left is called the remainder. A11 plus A12 plus dot 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 throughout eternity. Okay. This is the remainder term. What do we call this is the question, right? This is what we call R sub 10. Good. So notice that the R sub 10 starts with the 11th term. And you might think that's odd, but see, this thing cannot belong to both S10 and R10. You have to put it into one or the other. And it makes more sense to include it in our partial sum, right? First 10 terms. You get it? So for that reason, R10 starts with the 11 and forever. Those of you memorizing, this is a common mistake, okay? So far, so good? Okay, so you notice that our infinite sum S is made of S sub 10 plus R sub 10. Good. And that tells you R sub 10 is equal to S minus S sub 10. Right, that's what they call the error. Well, absolute value of this is called the error. This is known as the remainder, right? Because it's called the truncation error. If you only use the first 10 terms to figure out, estimate the series, then you're missing all of this, right? And hopefully that's a very small number, not infinity. Our convergence depends on this remainder part, right? So this is known as truncation error. You literally truncated something off from the infinite series, right? In applied math, there's a term. Okay, wow, so we can compute, oh, that's easy. We can compute the truncation error. So what is this? Estimate the error. We know exactly what it is. Do we really know what this truncation error is? Because this is a big science in applied math. Calculating the truncation error is one of the big deal. The way it's written, do we really know what truncation error is? We have the formula. Does that tell us what error is? What do you say? I'm going to tell you the analogous of the science class. Your science teacher told you that error is your true minus your measurement absolute value divided by your true times 100%, correct? Does that really tell us our error? These two are kind of same idea, right? True minus your estimation. And we are not doing it as a percentage here in numerical analysis. We just, figure out how big this is. In science, they usually want % error, so we calculate the percentage. What is wrong with this method? Somebody tell me. I am claiming this. You cannot compute your truncation error this way. You cannot, if you're a scientist, you cannot really compute your error of your experiment this way. Why not?
Because you can't get the actual value.
You don't know what this actual is. You don't know what well, this you know because you're a high school student. So if you look at the cover of your science textbook, it tells you what it is that you're supposed to be measuring. But if you're a scientist, I remember doing this Millikan oil drop experiment. Okay, in my physics class, also physics major on top of applied math. What that is Dr. Millikan has measured the charge of an electron for the first time in the history, and our lab was to duplicate that exactly, right? So we did a lot of this oil, charged oil, it flows in, I mean, because of the electric field and whatever. So we measure it. And then what is the immediate thing that you think I did? I opened the back cover of the physics book and look up the charge of electron to see if I got it right or not, right? Because I'm a student. Somebody has done this and won Nobel Prize probably on this already. But if you're Dr. Millikan, how do you know what it is that you're doing is correct or not? Right? This is like oxymoron concept. This only works in high school or college. But if you're the pioneer researcher trying to do this for the first time in history, this ain't gonna work, right? So like, forget that. There's a better way of doing error analysis, okay? That is the big science itself, the error, okay? Here, without knowing what this is, we still have to have a way of estimating this. Okay, that's the science. Because if before you build a program, I mean, this was an easy one to do, but if you're a NASA engineer, programmer, and there's a mission to Mars, and I was just told that they landed in Mars, or is it Venus? One of the two. Right, and this code will be thousands and thousands of pages. Before you do all that work, you need to know you can control this. If this thing gets out of hand, all that work is meaningless. You know what I'm saying? If you get the number and looks like we are getting 1 point something, but if you run it long enough, if this is 1.2 plus or minus, I mean, plus what? This better be not bigger than this thing. Our error must be a lot smaller than this. Otherwise, that calculation is meaningless. Do you know what I'm saying? Your measurement, your estimation has to be a lot bigger than the error. Otherwise, see global warming, right? Global temperature is rising. By how many degrees? 1 or 2 degrees. Is it 1 or is it 2? Plus or minus whatever. If it's rising by 2 degrees plus or minus 10, you know how useless that measurement is, right? So it's like that. Before, as a scientist, before you present something, you need to know with what certainty are you presenting this. And we'll never know what this is because there's no good formula for P-series. This is how it's done, exactly the way we did. So let's get into this science of error estimation. This is nice theoretically, but in reality, that ain't gonna work, okay? So I'm gonna draw some picture here, and on your homework, you have to draw some of this to start the series, and I told you there's a serious requirement, right? And this is why I required such a thing. Say our 1 over x to the cube function looks like this, right? So this is f of x is equal to 1 over x cubed. Good. Now we want this integral approximation to be above our error, correct? So what we have to do is draw these rectangles looking like this. This is the tail end of our sum. Let's use red. I'm going to throw one more. Okay, these are our rectangles. Good. Now, these rectangles start with, remember, R of 10 does not start with 10, it starts with 11. So this is rectangle number 11, and this is 12, and this is 13, and so on. Good. Each of this is represented with our AN, right? This is 1 over 11 cubed, this is 1 over 12 cubed, and this is 1 over 13 cubed, and we have to add that to eternity, which we can. So we are using, so S of 10 is this part, and this is R sub 10. You know what I'm saying? You know what I'm saying? Okay then. Now my question is, what is this number here? What is this number here in this corner? This is 11, isn't it? Our x value. And this is 12 and this is 13 because this is a right rectangle, 11 up there, 1 over 11. You know what I'm saying? So number here at this end, this is 10, correct? So far so good. In order to have this idea, R of 10, which really looks like this, integral, right, of n starting with 11th term to the infinity of 1 over n cubed. So far so good. And I want to have this thing less than or equal to something to the infinity, right? This is an integral test. This is why I did not want you to start just 1 to the infinity and integral test. No, no, no. This is what I was talking about. What should we start this lower limit with now in order to make it a fair comparison? This is my starting point. Right here. 10. Do you all see that it has to start from 10 in order to have exactly the same starting point for this race not to be rigged? So this thing is 10 here. Don't memorize it. I mean, it's like 10, 10, but it really starts with the 11th term. Good. You see that this number right here has to be 1 more than this number because it's a right rectangle. You have to draw it a few times to understand this. Good. You with me? Okay, after that, now we can say this is, now we have to convert it into proper integrals of b approaching infinity of b 10 to b and then x to the negative 3 dx. With me? Say yes. Okay then, now it's a downhill from this point. So that is equal to limit b approaching infinity of, this is x to the negative 2. Say yes. And then we put negative, I'm going to put it as a denominator. So x to the negative 2 over negative 2 like that. From b to, I'm screwing up, 10 to p. So far so good? Say yes. Okay. Now we substitute. You want to take 1/2 outside or not? Your choice. Let's take 1/2 outside. Limit b approaching infinity and use plumbing professor. Totally this minus that because of the negative sign. So we have 1 over 10 squared. Good. Minus 1 over b squared. You with me? Say yes. This could be very confusing. We take the limit, this dies, right? Thank God. So our error is under control if all we have to do is run enough numbers. You get it? If this thing blows up to infinity, you stop right there and say, okay, this series is divergent. Don't bother writing a program. Okay, so this is 1 over 200. Our error is accurate within. See, our remainder, this is our error, right? This is smaller than 1 over 200. So this is a very good approximation. You get it? You see how we can still control it? We don't know exactly what it is, but we know what the upper bound is. It's at most 1 over 200s. Say yes. Okay, then the last prompt. Last prompt is this. How many terms are required to make sure your sum is accurate to you? Right, this is 1/2000, is it? God, I should be good at this. I'm a math teacher. I cannot do this thing, converting this to, I think it's 1/2000, right? Yeah. How the hell am I gonna do this now? Right, okay. So let's go back to error analysis here. So what we want is now r to the nth power now in terms of n. And remember, if this is n, this is our n right here, right? But let's just think about this. This thing starts with n is equal to n plus 1 power really now, doesn't it? You see that? Because when it was 10, we have it starts with 11th power because s sub 10 is included, where an is included into the partial sum. Good? Say yes. Okay, well, of our 1/n cubed. Okay, that needs to be less than or equal to, tell me what this lower limit is. And then we can pretty much, this needs to be n, correct? Do you see this needs to be one more than this number? Did I put n is equal to n? You see that thingy makes no sense, right? Okay, I'm gonna change the index. Let's call it I. How about that? I mean, it doesn't matter, it's just a dummy index, but then I have to use I here. Yeah, because the problems dictates that's I, so we'll just do this. Do you like I better or K better? Some people like I, some people like J, some people like K. Your choice. I it is. Okay, I it is. That makes sense to you? Okay, then now we can do this part. This is a limit of b approaching infinity of n through b. These letters are not coming out clearly. And then x to the negative 3 dx, right? And we do exactly the same thing, so we can recycle our work. This is now limit of b approaching infinity of, so we have x to the negative 2 over negative 2 from n through b now. Good? Say yes. So we have 1/2 limit b approaching infinity of this one first, so we have 1/n squared minus 1/b squared, correct? Take the limit and this dies. So what we have is 1/2n squared 8. This is the size of our error. Truncation error. You get it? In terms of n. If we use n terms, this is what we are going to get. Remember, when we used 10, we got 1/200. Good? So all we have to do now is to set up our R of n needs to be less than our error, 1/2000. Good. All we have to do is solve that inequality now. And substituting, so 1/2n squared needs to be less than 1/2008, which means n squared needs to be greater than 1000. Too much algebra? You got this? Okay. But n is to be greater than what? And then, like, if you take a cube root, somebody take a cube root of this and tell me what cube root of, square root of 1000 is. Do you get 31 point something something something?
Yeah.
But remember, this is our index. It needs to be an integer. The question is how many terms, you know what I'm saying? So we have to put 32 to make sense, because this is the number that we are going to use as a k in our program. You know what I'm saying? So now this is the one, our input, this is our k. and run the program, then we have this kind of accuracy. Our truncation error is less than 1/2000. How about that? Pretty cool, huh? So as an applied mathematician, you have to run these things before to ensure the programmers, which is usually you, before you write it, before you have to ensure yourself. There's a future, there's a hope for this project. So go ahead and start coding. Otherwise, if this thing becomes infinity, then you have to report to the bosses. Okay, this is a stupid program. We should cancel this project altogether because it ain't gonna work. This is the job for applied mathematicians. You get it? Okay, and they work in conjunction with scientists and engineers all the time to do these kind of things. I mean, coding is a lot more complex than this, but essentially this is the idea. Any questions? Okay, in the Dropbox note, there's a thing called the improved estimate of the sum. Don't bother. I'm not gonna do that this year, okay? That is all about the finding. We have the upper bound, right? We can also find the lower bound of the error. So error can be at most something, but at least something, so in between. But during this pandemic, I don't think AP will ever ask you anything remotely close to that. So it's like, forget it altogether. We'll be glad that you can do the upper bound, okay? So that is the 30 and 31, the letter B part. I have taken it out already.